Greetings, happy coders. Welcome to another episode. And today we are doing a Let's Hack. This is the first of a series, well, we shall see, in which rather than playing a game, I'll be looking at hacking a game. Could be something that takes my fancy or something that is requested by someone on Patreon or something like that. Either way, let's take a look at the game. Let's start off like this. Now, as you can see, this is Z-Man 1983 DJL software. This fancy little basic generated logo here, probably kind of cute, isn't it? And you probably can guess what this is, and we'll take a quick look. This is the ultimate Spectrum version, so you know, the can't get better than this, basically. Let's have a little game. Okay, so I think you get the general idea. Now, this all came about from something that Stuart Campbell posted on Spectrum Computing forums. He was asking about Atarisoft Pac-Man, and this game is quite similar to that. Let's take a look at Atarisoft Pac-Man now. So this is Atarisoft Pac-Man. Certainly looks very similar, doesn't it? Yeah, I mean, basically it's the same game. I think what happened is that Atari decided that they were going to put out an official Pac-Man on the Spectrum. There was already dozens, literally dozens of clones of Pac-Man of various degrees of quality. And I suspect that they put pressure on to this company and worked out a deal which would basically save them money, probably get a lump sum to the people that created this, and as a result Atari would get a quick version of Pac-Man that they could use. All they have to do was slap the Atari logo on, change a few bits and pieces, and it would become an official Pac-Man game. And that's the reason why this Pac-Man is kind of, well, a little bit rubbish, frankly, because it was released a couple of years later than it was originally written. And basically, yeah, you're putting out a game in sort of 85, 86 when this game was written in 83, and it shows, doesn't it, really? So it's kind of interesting. It's not the only time this has happened. US Gold, obviously, perhaps most famously did that with World Cup Carnival. I can only imagine what some of the kind of school kids would have felt like when they thought, wow, this is the official Pac-Man. And then they bought it, and they had already, being a fan of Pac-Man 2 years earlier, they'd already bought this Z-Man, only to discover that it was more or less exactly the same game. And it is very similar in the sense that it has the sequences in between, you know, after every couple of maze and so on. But of course, what you'll really notice, and this is the point that Stuart was making, is that in this particular game, the maze is nothing like the original Pac-Man arcade maze. It's huge, basically. It's absolutely huge. Now, one of the things that they did to compensate for that, as far as I can tell, is that they made the power pill, how long the power pill lasts, a little bit longer, just so that you can actually kind of traverse the maze and survive. But yeah, you've got these tiny little graphics, which they're not terrible, but they're not great either. And this huge maze, and that kind of makes it not very frantic, really. It's not very Pac-Man. It just doesn't quite work. So Stuart wanted to know if I could, well, if anyone, basically, just put a call out, see if anyone could do it, and one of the guys chipped in with the location of the maze, and then I kind of got the ball, ran with it, did quite a few changes to try and make it look at least a bit more like Pac-Man, and let's move over and take a look at what I've done there. Okay, so as you can see already, I put the arcade font in there. Let's take a look at the game. Okay, so basically taken the maze and made it to be almost the same as the original Pac-Man maze, which is what Stuart suggested. I actually made it even narrower than his suggestion, and obviously the exits had to change, this had to change, and I'll go through, I'll show you the various steps that I took in order to make that previous game into this one. Didn't really change the engine. I do have plans to make a Pac-Man game myself at some point with smoother sprites and various bits and pieces. I may well get onto that fairly soon, but this was an interesting experiment. I thought I'd probably learn a few tricks going along. So yeah, I'll have a quick play for you just to show you how it all works. Here we go. Okay, so there, as you can see, it's a little more manic than the original being the original copy of the original. Anyway, the copy of the copy, I should say, of the original. We got there eventually, but yeah, so one thing I haven't done actually at this point is looked at the timer for the blue ghosts, because I think with this maze being what it is, the timer is actually a bit too long now. Makes the game very easy. You can get sort of through 3-4 screens without really feeling in any danger. So probably have a look at that, and maybe by the end of this video we'll have sorted that out. But yeah, let's go through step by step how we would do a hack of this kind. There are several different things that we need to do, and the first thing that we would do is change the size of the maze. And once we've done that, we will then look at what kind of problems that would actually throw up. So let's do that next. Okay, so here we are in Fuse, and I have opened a tap, which is from World of Spectrum. It's the original release on tap. Now the first thing that I would look at when I've got a tap here is I would browse it and get an idea of how the memory is being used. And as you can see here, 16386 bytes, which basically suggests to me this is very much a 16K game. So I'm actually going to test that out. I'm going to switch over to 16K, see if the game runs. So far so good. Terrible ghost, wasn't it? Okay, so let's pause it there. Clearly, what we're working with here is a 16K game, which is good news in the sense that we can use the other part of the memory to possibly make some additions, and also use it to run some routines to have a look at the part of the memory that's being used. So that's the next thing that we'll take a look at. Let's switch back to 48K though, and we'll do that just a second. Actually, I think what I'm going to do is let's reduce this beeper sound. It's getting a little bit too much. That means I can speak over it now, at least. actually. It's okay. So let's take a look now then. This is in Fuse. That most of the options for doing this kind of mods are available in Fuse. And we'll have a look at the memory browser here. We'll scroll down and you can see that's the ROM and here, and already we're getting a little bit of a clue here because this is the screen here. Okay. Look for patterns here. You can see today's greatest score, congratulations, and so on. This looks like it might be something to do with a maze. It's possible. That could be where the maze is stored. So that's a clue. And then you've got here, as you can see, everything above this point is empty. Obviously that's just residual from the Spectrum. So yeah, we're not using this. Now it's worth checking if it runs on a 16K, and the reason for that is that although a game might actually only be 16K, it might use the 48K memory area for a buffer, or for it might copy some memory over there for some reason to make the game run faster or something like that. So that's why I checked that it was running on a 16K machine, because then it doesn't have that memory available, so you know that it's not being used. So that's just a 100% confirmation that that's the case. So we're looking for the maze data here, and we have a suspicion already, I think, that this could be it here, because it's probably stored as a set of characters. And you can see here that if you look, you can sort of see there's a, if you look at these 47s here, you can kind of make out that there are lines here. Looks like 2 lines of 47, and then yeah, so I would definitely suspect that this would be the place to start. But what I'm going to do, well, to be honest, I've already done all this, but it's worth going through, showing you the things that I've done. So what I did is I saved off a binary. So let's do that now. So if you take a look at this memory map, which is from breakintoprogram.co.uk, we can see that the first part here is the ROM. Following that, we've got screen memory, then there's a printer buffer, system variables, and some reserved space. And we can load from 5ccB in hex. So I'm going to actually save it off from 5D00, because I think that's pretty much correct, and that definitely includes the area that I suspect is used for the map. So let's switch back. So basically we're going to save off that 16K, but before I do that, let me just bring this calculator in just to show you, if you are going to start playing about with sort of modding and hacking, then this calculator is going to be invaluable. It's the regular Windows calculator, but it has an option for programmer mode, and it's going to let you switch between hexadecimal, binary, and so on. So 5D00 is where I'm going to start from, and we can see that's 23808. We have to do this conversion because Fuse will only accept decimals when it comes to saving in binary, so we'll make that conversion there. So what I'll do is I'll put this into the memory, and we know that 32768 is the top of the memory for the 16K. So we'll just subtract one from the other, and we need 8960. So basically this game is only about 89K essentially in total. So yeah, 8960, so we'll call that 9000 roughly, that would do, and we'll save it off from 23808. So let's do that now. So I'll just put that in there like that. So 23808 and 9K roughly. Okay, so we've got the game binary now, and we can take a look at that using some tools that I've written on the Spectrum itself, And the reason I've done that is because although this memory browser is quite useful, and it does let you view the character text here as well, and it gives you certainly some idea of where you're looking, there is a nicer way that you can visualize this with a couple of little tools that I've written. I'm going to show you those now. Okay, so here's a bit of assembly. Now basically there are some hacking tools, sort of hex viewers and things like that, that you can use in Windows, and they are very useful, but I still think that you can't be using the actual machine itself for looking at the memory, because you get the visualization in the way that it would actually appear on the real machine itself. So I've created a small program here, and I'm not going to go into too much detail in terms of assembly, but I will explain exactly what it does so that you can see why I've got this program. It's a very short program. So the first thing I do with this program is, well, I'm going to run it up at 64768 up at the top of memory, so it's not interfering with our code. And the first thing I do is I fill the screen with stripes, so alternating on and off pixels. And the reason for that is that will become apparent because when you put attributes on screen, the two colors that are in the attribute will display on the screen. And basically this means that if we put memory onto the screen in terms of color, it will give us more or less a unique color for each different value that could be in the memory. So what I'm going to do here is, there are 768 bytes on a screen, and I'm going to browse through the memory by copying each part of the memory in turn, in steps, to the actual attributes, to the colors, and that will give me a color representation of all of the different areas within the memory in chunks of 768 bytes. So if there is some map data there, and it's likely to be uncompressed data, then we will see it on the screen and we'll have an idea about exactly where it is and how it works. Well, that's the plan anyway. Okay, so here we are back in an empty spectrum. First I'm going to load the binary data in at 23808. Hopefully I'm going to have no issues with that in terms of, because I haven't got any basic programs in there, so there shouldn't be any problem. Then I'm going to load my binary data in here. And if I now execute that code, I should be able to, oops. Okay, so what I've set this up so that I can go through one by one each part of the memory, and you can see here immediately this is the second block of code, and you can see there's definitely something here. This definitely looks like the Pac-Man maze, and here for sure, and this absolutely 100% is definitely the Pac-Man maze, isn't it, right there? So you can see two sections, looks like there's colors for the ghost just there. Okay, the rest of the memory there isn't much else. This is an interesting pattern here, we'll come back to that a bit later. So basically when you're visualizing things, you with practice you kind of learn how to kind of recognize things within the code when you're looking at numbers. So code itself, actual machine code language, the actual programs, that kind of data tends to be very, very random, because the various different commands that are being used are spread right across the number scale, whereas data like graphic data or character set data, things like this, they have very specific repeating patterns which you can recognize. That's why when I looked there at the very end of the memory, I noticed a slightly different pattern, which indicates to me that that might be some kind of data rather than code, because as you could see, the code itself, I mean, if I just I will run it again in a second. I'm going to make an adjustment, so let's just run it again, in fact. So Okay, so this is kind of what code would look like. It's very random, whole kind of different colors. And here you can see there's a very much of repeating patterns. This very much looks like data. And so what I can see here as well is this looks like here, or possibly here, is where the screen probably begins. And if we switch back to the actual screen itself, you can see here that there is a line here for the score and there's a bottom line here. So we know that the map itself is actually not full screen. It's only 22 sort of rows rather than 24. And that should become a bit more apparent if I go to the next screen here. And if I line those up, we can actually see there, if you can see that, that's definitely matching up in terms of colors. Here there's an exit and so on. And if I look on the next half there, here we can see, I can pull that up or down. Well, I can actually, I guess I'll put one corner next to the other there, you can see. And there is definitely a bottom row here, and look, you can even see here there's color. And this looks like the colors for which are being used for this thing down here, which immediately leads me to try something else, which would be to load this screen into something like ZX Paintbrush and take a look at this screen without the attributes. So in fact we could do that even within the spectrum itself. So let's do that. We'll save a binary. Save off 16384 and we'll just save the pixel data, which is 6144 bytes, like that. And so if we reset, and we want to 8K mode here, but that doesn't matter. So what I'm going to do is I'll load this binary in now at 16384. Okay, and there you go. So this is the screen without the attributes, and what we can see immediately here is that the attributes are masking or hiding the bonus. So what the coder has done here is each level will have basically all of this data is already in there, but the player can't see it. And the same for the lives. So that's quite an efficient way of doing that. It means that you only need to have one screen for the whole game and just load it in one time, and that's fine. You see the score is up here, and if we are able to go back and look at the let me just see if I can put that back there. Yeah, so you can see, look here, this is the colors that corresponds to these here. So that's another clue. That helps us a little bit more, and we can be pretty sure here now that that what we've got here, I'll have to just flick through, but again, just for reference, as you can see, this is game code. It's very random. There's not many repeating patterns. There might be something a little bit here, something going on here. This looks slightly mazy, doesn't it? Possibly there might be something at the end here. Could be something like maybe a collision map or something like that. And here this looks different again. Doesn't look like code, so there might be something at the end. There could be some graphic data, maybe something like that. So yeah, one thing I've done in the code is I've set the border to change each time I press a key when I'm looking at empty memory. I could improve this and sort of make it so that I could browse through or quit or whatever, but it's very quick. You can just basically really just flush through the memory super quickly, and that's obviously helpful because all the time when you're doing this, and it's a very fun kind of hobby, is just to look for the clues and then follow the clues, and then little by little you're working out where everything is and getting closer to what you're looking for. So we'll just run this one more time, because I want to now look at where this memory starts, which is just here. And if we count down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, I think that is. So that means I need to add 15 times 32 to get this to display at exactly the right position. That should be how it works. We'll figure that out now. So if we come back to our calculator, and we know that there are 15, it's 15 down, so that would be 0 to 14. So 14 times 32 would be 448. And we'll add that to our original number here to give us 24256. And then, so we'll go into here, 24256 in here, and now we'll just compile this and load it back into the spectrum. Okay, so we'll load the, we just need to basically load it over the top again. So it's this one here. And then we just run it. Okay, that's the first part of our code, right, and there you go. So here we can see this is basically our map, and this part here is the second half of the map, and clearly this is the attributes. So what one would immediately suspect then is that the first part is showing the character, like some kind of a UDG like character set, because all the graphics are done. You can clearly see, as I just skip past this, I'll explain more fully just a second. So yeah, basically we take another look at the game and you can see that everything is done in 8x8 squares. So everything is done in 8x8 squares clearly here. So the way that this map is drawn, it's definitely going to be drawing sets of 8x8 characters. Now it could be using its own routine, but because this is a 16K game especially, I would strongly suspect that it's using the ROM. Now obviously I've done this hack already and I know that it's using the ROM, but again, the first thing you do is think logically. Probably it's going to be using the ROM because the memory is going to be an issue. To get it into 16K, they're almost certainly going to be using the ROMs. But there are some ways that we can absolutely confirm that that's the case, and I'll show you how we can do that. So what I'm going to do is I'm going to reset the game back to before the screen is drawn, and I'm going to look at this point of screen memory and see when it's being written to, this first point here, and from there we should be able to figure out exactly what routine is being used to draw this, and that will then give us confirmation as to how the graphic data is stored, and if we know how it's stored, then we can write a routine to help us locate it more easily. Okay, so I'm about to run the game here, and this would be the very top of the pixel memory here, and I'm gonna basically go down one character. So this involves adding just 32 bytes, 16416. So inside of Fuse here, within the debugger, I can put a break option in here. Now if I put BRW, it means break when written to, and I'm going to put 16416 in here, and that will basically stop the code when this byte on screen is written to. Now obviously when we start the game, it's going to clear the screen first of all, so that won't be the thing that we're looking for. If I just unpause it now, there you can see it's immediately broken, and it's basically doing a clear screen here, so we don't need to worry about that. But you can see that that's also a ROM routine, which is interesting, but not immediately what we need. And then here it's broken again. You see the screen's been cleared, and now it's drawing. It's actually drawing the map, and this is the start of the map, and you can see basically here it's using this area of the ROM. And if you know the ROM, this is basically the character draw routine. So that basically tells us right now that we know that we are effectively using ROM to draw the map. And that means that it's going to be stored in like UDG style. And it also means that it's probably going to be reading, well, it will be reading from the system font. And we know that the system, well, it will be the system font, but in this case it will have reassigned the font to a different location in order to draw the map. So basically we need to look at this memory address, which is a system variable, which tells us where the font is being stored, the one that's currently in use. So that's at 5C36. So if we come back into here and go to the memory browser, we need to go down to 5C36, which is just here. And if you take a look here, so 0, 1, 2, 3, 4, 5, 6, and it's these two numbers here, 7C00, right? And that tells us this is the location of the character set that is currently in use. And we know that it's drawing the map right now, so that means that we know that the map data starts at 7C00 plus 256, because the first set of characters, the first 256 bytes, 32 characters, is not used. So let's take a look at that. So here's the calculator, and this is going to tell us 31744. We add 56 to that, and we get 32,000, and that tells us the location of the character set. At least we can be pretty sure that that's where it is, but of course we can easily confirm that using some code, and I'm going to show you that now. So this is the second part of the tool here, which is used for displaying data in character set format. I'll talk you through this. I'm afraid I haven't annotated it, but I will do, because I'll release this as part of, alongside the video. So basically, this is a very similar routine, but what this does is it looks at 256 characters and displays them in character format. So it's about 2K at once. It will show it in the top third of the screen, and you can basically browse through the memory looking for fonts, looking for UDGs, user-defined graphics, things like this. Now, I've actually set it to start at 32,000 because obviously we worked that out. We know that that's the start of the code. Well, we certainly very, very strongly suspect that that's the case. And what this basically does here, you can see duplicate 8 here. It basically draws the characters in the format that they're drawn by the ROM. So basically 1 by 1 square, 1, 2, 3, 4, working across like that. As I said, I don't really want to go into too much detail here. If you understand the code, you'll know what that means. All I can tell you is that we're basically writing the data to the screen in the same format as the ROM would use. So we are basically doing a loop, which is allowing us to flick and browse through all of the memory and trying to locate the characters. But we strongly suspect that it's here. So we can now move across and run that code. Okay, so we're back here with the Spectrum, and I'm now going to run the code at 64809, which is where this viewer is held. And there you go. Immediately you can see that we have got the character set that is in use, and we can see that we've got the Pac-Man, we've got some score here, we've got even this little ready thing here. It looks like that's basically kept there permanently within the screen, perhaps, and rather than printing it as a text. And then we've got here the various bits and pieces. There's the bits that are used for the map, Pac-Man, the ghost, and the death sequence. So That's basically it, and there's nothing else in the rest of the memory, as you can see. So that confirms what we already suspected. So that means that we now have the location of where the map is stored. We know that it's using the ROM, and we also have the location of the character set, all of which means that we could now use that data and load it into something like AGD, the editor, because I know the format, I know AGD very well, and I can use that to basically load the data in and see if we can actually view it on the screen. So let's take a look at that now. So here we are in AGD. Now obviously I've written AGDX, I should say. I've written a lot of editing sort of routines for this, and it does have a really good block editor now and screen editor that I can use to look at other games. It's actually the way that I did things like Bruce Lee RX and Perils of Willy and so on. I use it quite extensively. So what I'm going to do basically now is we'll go to here. I need to create a set of blocks. Like so. There we go, we've got 128. And then all we need to do is get our data out. So let me switch back over to the Pac-Man game. And I'm now going to save character set. Here, 768 bytes. This is purely pixel data, of course. It seems that the colors are actually put in there using the second half of that memory map. If you remember the memory map with the colors, it seems that the colors are, it's like an overlay. Essentially, it's an overlay. So we know we can probably deal with that as well quite easily. So now we've got that, let's go back to the AGDX and have a look and see if we can load this in. Okay, so here we are. And let's load the binary data. Now, this number here tells us where the block data is stored in AGDX, so we just need to load it in at that address. Okay, we'll reset and come back in, and there you go. So I've actually overshot. We didn't need 8 sets, we only needed 6 rows of characters, so don't need to worry about that. Now obviously there's no color in here, and essentially we're going to have to put that in manually, but it's not going to take very long because obviously the colors are yeah, I'll just go through. I would have just gone through and loaded the colors in manually, so I'll come back to that. Obviously you don't need to watch me do that. So yeah, so that's that part of it. Now the other thing that we want to do then is see if we can get the window, the map, to load. So I'm going to set the screen up here, which is the equivalent of this. I'm not going to worry about these top 2 rows. This part was obviously held the score, and this part was holding the data for the lives and the bonus items and so on. So I'm really just concerned with the map, so I'm going to set it up like that. Okay, and if we go to the editor, here right now what I know is that I can load in an uncompressed version of the data into here in such a way that it will display correctly. But there is a catch here, and that catch is that because this is using characters, using the ROM font, we know in fact that block 0 is not going to be block 0, it's going to be block 32. So essentially what that means then is that I need to load the data in at this address rather than here. So let's look at doing that now. Three seven three six. Oh. Okay, so we'll come back and we'll look. Okay, so now we've basically got it loaded in here, and obviously I'd have to just wipe through all of this. So just in case that isn't clear, kind of thinking on my feet here, but basically the font, obviously the first 256 bytes here are not used. In other words, the map data, as we've seen the map data on the screen, it's not going to be sending char 0 to print here. It's going to be printing char 32. So we know that it's going to be using the ROM, so we know that it's going to be using character codes, which means the character code for the empty space is actually going to be 32. It's not going to be 0. In AGD it's 0, so that's why we need to put that offset into there to make that work. Alright, so we already figured out where the map was stored, so we know that that's held at the address. I'll just go back and double check. Hang on a second. So if we go back to our screen here, you'll remember that we were looking at the graphical display from 24256, and it was actually the second screen that displayed the map. So if I bring that up now, I'll just show you that one more time. So there was code here, and then this was our map data right here. So what that basically means then, and that's our color data right there. So we'll just skip past this. Oh, we'll just take that out of the way. So basically what we're doing now is this number 24256 is here. We go one screen ahead. This will tell us where the actual map data begins, and plus 32, because obviously there's one row which is for the score. So 25056 will be the address that we use for the actual map data. So we'll jump back to the game now and we'll have a look at that. So here we are in the game, and I'm now going to save off a binary at 25056 map bin, like that. And this will be 768 would be the total, but the top row is 32, so we'll take that off, and we don't need the bottom row, so we'll take that off, which means subtracting 64, which gives us 704 bytes. So we'll save that off now. It's just Fuse misbehaving itself a little bit. In addition to that, we also know that the color data is stored at 25824. Now we can't actually bring that into AGD, but we can test it out just to make sure it looks okay. So I'll save that off as well, 25824. Call that overlay. And that's also 704 bytes. Okay, let's switch over to AGD. Now, when you're editing a screen in AGD, I know that at the top of the memory at 64768 there is uncompressed data for the map, which means that I can load this binary in here, this one 25056. If I load this in at 64768 and then refresh it, there you can see we now have the map as it appears in the game. So that's the game data, that's the actual map that the game starts out with. And yeah, that's pretty cool, isn't it? So what next? Well, obviously we need to try the color. So what I'll do is I will try the overlay. Let's just try this out. So this would be 22528, but I'm just going to load it into the color. It would be 22528 with a plus 32, so that would be 22560. And if I load that into there, you can see it's basically colored it in. Now that's not something that I can edit right now with those colors. It's just confirming what we already pretty much knew, was that the overlay was in there. So that's how that would work. It's still black and white, as you can see here. But all that I would now have to do is go into here and make a few changes, make a few quick changes like this. That would be pretty straightforward. Might as well. Well, I'll deal with that later. Do put all the colors in later, of course. Incidentally, what I can also do is I can edit the graphics as well if I want to, which is what we'll do later. But let's take a look, and now you can see very clearly that we've got ourselves a full Pac-Man map as it's displayed in the game. And obviously what I can do if I want to now is I can create another screen and I can draw my own map using the blocks that are available in here. So essentially what that would mean is I could just draw something like this. Oops. I was going to write hello, but I'm not going to spend all the time doing that. I'll just write HE, okay? Now, let's just see what happens. If I save this binary data, we'll put in here 2506 map edit. Okay, and we will save it from 64768, and it will be 704 bytes, right? We haven't done anything with the color, but we won't worry about that for now. Okay, so let's switch back to the game and see what happens. Okay, so here we are in the game. Let's load the binary data. And map edit 25056. And okay, well, there you go. You can see that it has more or less worked. You can see the H and the E here. The issue that we have is that this empty space is being filled. It's just completely empty. It's stored it as character 0 rather than character 32. You see, that's the reason why that's the issue here. If we go back here, you see this, all of this area is character 0. That's standard in AGD. So what we'll do is we need to actually use this one. So if I just put a little marker on here like this, you'll see there, right? But I don't want to do that. I don't want to use that character because that's what's causing the problem. We need to use the character 32. So we'll go to 32 here and we'll just press replace like that. And that should now, if we now save the binary data, do it again. One more time. And we'll save this at 64768 and 704 bytes, like that. And we'll go back to the game. So this is the game again with the fresh copy. I've just restarted it. Okay, now let's load that data in at 25056. Okay, let's see what happens. There you go. Alright, so the game has basically crashed because it doesn't know what to do with this data, but as you can see, we are now able to edit the game, edit the maze from within AGD, draw exactly as we want, create the map, and then from there adapt the game to suit the map. And obviously, if we shift back to here, what we will be able to do is, this is of course displaying the map as it should be. We could save off the screen memory here, and that will be our overlay, so that will also be correct from here, so we don't actually need the colors. The colors will of course assist us when it comes to designing the maze and making it look right. Okay, well, I think that's enough for part 1. We've done quite a lot. We now got to the stage where we can edit the graphics and edit the map, and so in the next part we'll look at creating the map itself and then adapting the game to make it run correctly. So stay safe, and as always, happy coding. Bye bye. This video would not be possible without the amazing contributions from the people whose names you can see scrolling up the screen right now. If you'd like to be one of them, you can get all my games for free. You can get some coding tips. You can even get to dictate which games I work on in the future, and you might even feature in them. So if that sounds good to you, then head over to the Patreon page. The link is just coming up now. And in the meantime, happy coding. Bye bye.